Excuse me. So I went ahead and started the live stream just so I don't forget to do it later. We're going to be talking about center of mass today, which is on page 43 in workbook volume 2. So go ahead and take a look at that while I get settled in here, clicking some buttons. Okay. And then I think I had some old playlists I was going to share with you. I think I sent that in a Canvas announcement already. I sent out a couple of Canvas announcements earlier today with some center of mass videos. And I think you could read those announcements after class. I think they might supplement what we're doing here, but yeah. Yeah, I think one of them was actually a good summary. So in case I forget to do a summary at the end, you could watch that later. So for now, let's maybe start. Let's get me up there. All right. So first off is center of mass. Why care? So why care about COM, center of mass? All right. So if you think about it, here's one example. Take this eraser. If I throw it and spin it, as it's flying through the air and spinning, whoops, it spins about its center of mass. Now, this particular object is fairly simple, right? We know the center of mass of this is probably right in the middle of it because it's a uniform object made out of foam, but there are two dissimilar types of foam there, so maybe it shifted a little bit one way or the other. But this is one reason. Not always, but objects tend to rotate about their center of mass. So that's one reason why this is useful in a rotation chapter. Number two, if you're doing a gravitational problem with a pendulum, let's say, pivoted about one end and it's attached to the ceiling, if you needed to calculate the gravitational force or the gravitational energy, that matters based on the center of mass height. So the center of mass is the height that you should use for your reference levels. So when it swings downwards, maybe to the bottom of the swing, as it swings down to the bottom of the swing, it doesn't matter how far the tip has moved. What matters is how far the center of mass has changed. That determines the change in gravitational potential energy. Or similarly, if you're trying to analyze a torque problem, right? If you want to figure out the angular acceleration, again, this is chapter 10 stuff, but you need to understand center mass for doing chapter 10 and chapter 12. And I think maybe even a little bit in chapter 13 and etc. So it's used in other chapters. And finally, the math of center of mass is similar to physics 163 when we're doing charge distributions. It's also similar to physics 162 when you're doing probability distributions. By that, I mean quantum mechanics, the probability of an electron being in different places. There's a thing called a probability density function. So when we deal with center of mass, one, there's practical nuts and bolts that relate to this chapter, but the math is also foreshadowing other classes. In particular, probabilities are very similar to densities, and the types of calculations we do are similar to these. Okay, so there's a number of reasons we should care. There they are. Great. Now, if you got, let me go ahead and bring this up here. Whoops, wrong screen. Whoops, that's the wrong, whoops, that's for later. Wrong screen. Obviously, you could code the center of mass too. That's what I was, that's for later. Sorry about that. Let me get this one up. All right, and so let me scroll back a bit here. What did I say? Page 43, I think, right? Almost there. I suppose I should have just gone to there. So This strategy, and I'm going to zoom out just so it's all fits on one page. This is the stuff that I want you to internalize, all of that, which that is not obvious. Obviously, it's way too small to read right now, but I don't know any shorter way than to say you need to be an expert at all of this stuff to understand center mass. You might think you understand it from a math class, but let's face it, math people just do this, give this window dressing, and that's all they should do. They're not forced to use this regularly, right? Whereas engineers, physicists, we actually use the center of mass, so we need to understand it more deeply than a cheesy math calculus class. All right. All right. So we're going to start by analyzing these first three, and then we'll do a couple of worked problems. Then we'll come back and analyze this fourth one. So basically, we're going to see there's a number of different tricks we can use to avoid using calculus. If we could do that, we want to use these tricks. And then if we have to use calculus, we need to understand all of that junk down there. All right, so let me just start here. If I drew a rectangular plate, and let's say I made this out of aluminum, okay, let's say, or a piece of cardboard or a piece of paper, most of you would have no trouble just saying, well, isn't the center of mass right in the middle? And you would be right. Why would you do calculus when you just know intuitively where the answer is? Now, what if I drew a circle, a circular plate? Again, you'd probably have no trouble saying, well, the center of mass is right in the middle. And so for those types of things, you should not do any work. You should just write down the answer. Don't think too much about it. However, what if we did a triangle? And I want to figure out the center of mass. This one might not be so obvious. However, if we look at bullet 2, I'm going to just tell you the answer to this one and you can memorize it. We'll derive it later in today's class in case you're wondering where I get this from. But look, we're going to memorize the answer for this one. So it says it's 1/3 from the fat end of the triangle. So what does that mean? I'm telling you, if I split this into thirds, those aren't exactly thirds, but, and then here, this is a right triangle. If you have a right triangle, the center of mass is 1/3 from the fat end in each direction. So it's 1/3 over and 1/3 up. Cool. Obviously, if the triangle was reoriented in a different way, say like this, and it could have different, dimensions and such. But again, we would say, well, split this into thirds. It's 1/3 from the fat end. So that's why I remember it that way. This is good no matter how the triangle is oriented. In a math class, they always give you this one and then never challenge you and say, well, what happens? How do you do the math if it's not exactly like this? Well, I'm going to show you. All right. So first is have it, just look at it and know the answer intuitively. Second is have the answers for common shapes, circles, triangles, squares, etc., memorized. 1/3 from the fat end. What's the next one? Try to build up an object out of several known shapes. And if it's an object with a hole cut in it, you could use a negative density or negative mass, and I'll explain what I mean. So what we're going to do is we're going to split up an object into several pieces and do it. Let me just show you one. Let's say we had a circular plate, and then I attached to that circular plate a triangle plate like this. I don't know, for some reason, let's say you do this one. Now, I know the center of mass of this one is right at its center. I know the center of mass of this one is 1/3 from the fat end each way. So there's center 1, and I'm just eyeballing it now. The idea is I'm going to put a coordinate system on here. Let's just say this is my coordinate system. You could use any coordinate system you want. I just picked a random one. The idea is this distance right here would be x1, the horizontal position of the center mass. Obviously, you could also do y1, but for right now, let's just stick with the x coordinate. This distance right here would be x2, the horizontal distance to this object's center of mass. And then the total object's center of mass would be x center of mass is equal to, we take x1 m1 over m1 and x2 m2 over m2. So we get the total mass on the bottom and each different center of mass multiplied by its mass. You could think of this like weighted grades. The idea is this might be the weight of an exam. Like, let's say your exams are worth 30% each, or one of them's worth 30, one of them's worth 20, and one of them's worth 50. Whatever. There could be different percentages, or your lab grade versus your lecture grade versus your final exam grade. So the idea is X might be your score, your position, and M would be the relative weights of those different scores or the relative masses of these different objects. If you've ever seen this in sigma notation, it looks like the sum of X sub I, M sub I, all over the sum of each M sub I. So that, and again, maybe you're used to seeing the things written here. This would be from I equals 1 to n. And here I would say I equals 1 to n. But yeah, this is how it might look in sigma notation. The idea is it's the weighted positions over the total mass. All right. Any questions about that right now? Here's something fun for you. When we go to calculus, this is what it's going to look like. A sum becomes an integral, right? An integral is a fancy way of doing a sum. So when we go to calculus land, it will look exactly the same if you think of the integral as the sum, dm as a small amount of mass associated with one piece of the object, x being the position of that object. And it's the same thing. All right. Now, and the same idea, like I said, what if you cut a hole out of this? If you cut a hole out of this, let's say that purple section was a hole, you could just write in another section minus x3 m3 and minus m3. So if you had holes in here, that's how you would accommodate missing chunks. And by doing this, that skips a lot of complicated calculus. So hopefully we can use these tricks. And we're going to do examples in a minute of most of these different scenarios. Okay, so let's go back to the, let's see. Okay, and so now we're ready to do some examples. After this, if none of these first three bullet points work, if we can't memorize it or build it out of known shapes, we're going to have to use calculus. Let's do that in a minute. Let's start off with a simple one. All right. So let's look at 9.27. And I'm going to make this a little bigger. Each tick mark is 20. The masses are 1, 2, and 3. So in this case, we've got masses. Each of these tick marks is 20 centimeters. The masses are 1 kilogram, 2 kilograms, and 3 kilograms, respectively. I'm going to make it even one bigger. I think I can get it all in there. All right. So in this case, our center of mass formula, I'm going to write on the screen here for a minute. We want to use this center of mass formula right here. X center of mass is equal to the sum of x sub I, m sub I, all over the sum of the mass. Now, in this case, what is x1 here? What is the position of 1?
-1?
Minus 20.
4.
Centimeters. We need units too. Are you okay with that?
Yeah.
So one of the things we see is that in a math class, they're always lazy about units, right? In this class, we can't be lazy. So x1 is -20, and mass 1, I'm assuming, is 1 kilogram. All right. Ignore sig figs for the minute, just to save time writing. So x2 is going to be what? 40 positive centimeters, because it's a position. It has units of centimeters in this case. And finally, we have x3 down here. That's going to be what? 20, 40, 60, -60. So right now, obviously, you could do the same thing for y1, y2, and y3. For example, y1 would equal positive 60, y2 would equal -20 centimeters, and y3 would equal -40 centimeters. All right. So in this case, don't overthink it. And actually, to save some time, I'm going to go to the solutions. Let's see, where are those solutions? Whoops. What problem was this?
9.27.
Thanks. Oh my gosh, that last one was brutal. All right. Oh, I forgot to take a guess. Well, we'll worry about that later. Okay, so here's how the numbers turn out. There's the first line of the equation. Here's that with all the numbers plugged in. Notice we're being lazy with sig figs. And there, when you plug all that stuff in, notice what happened to the kilograms. Kilograms, kilograms, kilograms in the top cancels kilograms in the bottom. So notice X, center of mass, position is -20 centimeters. There's an implied I hat on that, right? Okay. I did similar work right here with the Y values, and notice I got this. All right. So in this case, let's go back and look at this and see what it means physically. -20, -17. Let's go back to right here. So -20, -17 is saying somewhere right about here. That's where the center of mass is. Does this seem reasonable? What do you think?
Yeah, because 3 is a bigger mass, so it kind of shifts towards it.
That's what we would think. Just like if you have grades, if you get a really good score on the final and the final is worth most of your grade, that should shift your grade up. But if you get a really bad grade on the final, that could shift your grade down. So these, you kind of know this intuitively, right? Same idea here. It's closest to the biggest mass. Now, if I split this thing, let me make a line here. We know the center of mass is on this line. Whoops, approximately, if I had drawn correctly, but it's on that vertical line there. Now, according to this, do we have the same amount of mass to the left and to the right of the center of mass? What do you think? Is there the same amount of mass left and right of that red line?
Yes, if it's the center.
Say again?
If it's the center, yes.
Well, do you agree 1 is right on the center? So 1, there's the same amount on either side. It's basically right on the axis. So we could ignore it. Do we have the same amount of mass left and right?
No.
No. In general, the center of mass does not split the mass in two. I'm going to say that again. We often think of the center of mass as being half the mass is on this side and half the mass is the other. That is a completely wrong way to think. It just doesn't work that way. It does for a rectangle, it does for a circle, but not much else. Okay. In general, if you cut something in half at the center of mass, you'll have more mass in one half than the other. Not always true. Some shapes are symmetric. Okay, just be aware of that. Let's bring this back down to more reasonable here. All right. So that's 9.27. I don't know. Any questions about that while we've got it?
So they wouldn't weigh the same if you were to split that because there's more.
There would be 3 on one side, 2 on the other, and 1 is right on the dividing line. So even if you wanted to, you could split up to 1 and you'd have 2.5 on one side, 3.5 on the other. There wouldn't be the same amount of mass on either side. Same thing with the dividing line vertically, right? Think if we use the dividing line vertically, it's even more obvious. The dividing line vertically is right there, just above the 2. So notice you have 1 kilogram way up there and then basically 5 kilograms down low. So the center of mass is not going to split the masses equally. The center of mass relates to this. It's what it is. It's the center of mass. It actually relates to torque, and we'll talk more about that in chapter 10. Is that good?
Yeah.
Here's another example, just to emphasize that. A mobile, right? Because we all build mobiles out of bowling balls, which is ridiculous, but whatever. In theory, you could build a mobile out of bowling balls. I wouldn't hang it above your baby's crib. But yeah, the idea here is, these masses are not going to be equal. For example, weight 1, we're told, is 16 pounds. And we're told that this one over here, weight 2, is 8 pounds. And we need this to balance that. Well, just think about it. We're going to talk about this when we do torque. This line looks longer than that line. And so depending how much mass you use for one of these objects, you need less mass if the other mass is farther away, things like that. Again, this is very difficult to explain without chapter 10. That's the next chapter. So let's save that description for then. Still, this is a straight up center of mass problem if you want to do another one, just to see where things balance with realistic numbers here. Okay. We're going to come back to the calculus. Going to come back to that. Let's look at 9.31. All right. In this one, how would you attack this one? What do you think? I'll let you think about it while I get it drawn up.
Is it better to split it up in like 3 different parts?
That's what I would do. I would split this into 3 parts. So, for example, you can kind of see it. Actually, let me just write it up on the board. It's faster. Now, you could split it into 2 if you wanted, but I like 3. There's one part, one rectangle. That's really easy. Here's this part. We'll do a different type of hatching there. Right? And then maybe over here, we'll dot this one in. There's the third one. Now, the idea here is I know the center of mass of this one, right, is right in its center. I know the center of mass of this one is right at its center. And this one is a triangle from what I told you earlier. It's 1/3 and 1/3. That is the center of mass of that one. So we've got these three pieces. Notice, I don't know if you've seen this yet, but I'm trying to do this in every problem, or hopefully remembering, is I'm putting a coordinate system on everything. If you want to talk about center mass, it's a lot like forces. You need to tell people what coordinate system you're using, because somebody else might choose this corner, somebody might choose here, somebody might choose there. I chose right here for reasons that will become obvious later. You could choose different coordinate systems in general, but you should at least draw it so I can follow your work. If you don't draw a coordinate system, your number is meaningless to other people. All right, so we're going to do this. X center of mass equals let me scoot this over a little bit. I need X1, M1. I need M1 in the basement. X2, M2. I need M2 in the basement. And X3, M3. We have three pieces. We're going to split it up. We need to do this trick again. All right. Now, I think, let me get the dimensions on this picture. Sorry, I forgot to write them. Where is that one? So it's C, D, A, B. Okay. Oh, okay. So this side is A. This side is B. This part was C. And this part up here was D, I think. Okay.
Isn't there only a M3 at the bottom? You have X3, M3.
Whoops. Yes, you're right. Thank you. Right there. Absolutely. Thank you for catching that. All right. So again, yes, you're absolutely right. We would have caught that when we checked the units later, but yeah, better to catch it early. So this is total mass on the bottom. And so that X3 makes no sense at all. You're right. Good job. Okay. So help me out here. I'm assuming this is object 1. This one is object 2, the bottom one. And this one over here is object 3. So what is X1? What would I have to plug in for X1? What does X1 mean here? It means the X position, center of mass of object 1. What is that going to be?
Is it A1?
Is that the X position? A relates to the height.
Is it C half?
It's not
Negative?
C over 2, but what is it?
Negative?
Negative C over 2. It's halfway there. So it's C over 2 negative in the I hat. Is that making some sense?
Yeah.
Okay, cool. All right. And so now what is X2? I think it's the same, isn't it? Yeah. The X coordinate is the same. The Y coordinates would be different, but not the X. And what is X3?
Negative D over 3.
Positive D over 3. The origin's right here, right?
Oh, yeah.
Yep. So what do we have to watch out for? We got to watch out that it's a triangle, so it's D over 3, and then positive because that one's on the right side. Now notice these are algebraic, so we don't need units on these ones, right? Because in theory, C would be some number that would have units. So if you plugged in numbers, the number that you plug in would have the units. All right, so now what's mass 1?
Wait, sorry. Why is
Go for it.
D over 3 positive instead of negative?
This is where I drew the coordinate system. Do you see it in there?
Oh, okay. Gotcha. Gotcha.
So it's in the first quadrant.
Gotcha.
Cool. All right. Other questions or okay, what's the mass? What's mass 1?
Would they all be the same because the same density?
They have the same density, but are 2 pieces of aluminum in general the same mass? You could have a big piece and a small piece. Yeah. You're on the right track though. The trick is, and this is crazy, this problem would work whether it's made out of cardboard or aluminum. The density shouldn't matter. So what we do is we rewrite the mass in terms of density, even though we don't know what that density is, and we should discover the density pops out. Think about it. This mass, all of these masses in here will involve the density. And because this is a uniform object, and let me show you what I mean by that in the wording. Right here, it says it has uniform density. What does that sentence mean? It means every piece of this object here, here, every little piece of it has the same density. The density is uniform throughout the object. So that allows us to rewrite the masses in terms of the densities. Density will be in every single term and it will drop out. All right, that's the trick. So now in this case, I'm actually going to use sigma for the density. Normally we use rho. Now I'll explain this in just a minute. And actually we know all of them have the same density, so I don't even need a subscript on here. This is sigma, lowercase sigma. Circle, horizontal line. Okay. So let's check the units of what this means. This is kilograms. This is meters squared. It's an area. What do the units have to be for sigma to work out?
Kilograms over meter squared?
Yep. So this is called an area density. So it's talking about how many kilograms per meter squared. For plates, this is the logical density to use. If you've ever looked at moving trucks, you could buy space on a moving truck. You could pay per foot. You're getting a volume, but you only pay per foot. Or if you're buying rope or cable, sometimes you pay for it per foot. Well, similarly, if you're buying aluminum plates, they charge you by the area effectively. Now you're getting a volume. Even this piece of paper here that has all the answers to your final exam, just kidding. This piece of paper, even though it's super thin, does have some finite thickness. So we could treat this as a volume, but it's a lot easier for these center mass calculations to treat it as an area, right? Because it's uniform thickness throughout. All right, whatever, enough on that. So now, okay, I talked about the units. I will discuss this more when we get to the calculus part in the last half of today's class. So this is mass 1, sigma area 1. All right, great. So now what about mass 2? That would be sigma times area 2. And mass 3 similarly would equal sigma times area 3. Area 1 would be AC. Area 2 would be BC. And area 3 would be what? What's the area of object 3 there?
AD over 2.
Yep, AD over 2. And so now I'm going to pop into the solutions and take a look. Whoops. One more. Almost there. Oh my gosh. You can see why we're skipping the calculus to start. There it is. So in this case, this is how I got those masses. This is how I got these positions. I think we labeled them the same. And when you plug it all in, let me make this just a little smaller here. There, it's all on one page. I hope you could read that. Sorry if it's too small. You can let me know. All right. So in this case, let's see, this is the final answer right down there. But notice you just plug in mass 1, x1. Mass 2, x2. By the way, there's mass 2 on the bottom. There's mass 1 on the bottom. And then finally we have mass 3, x3, and there's mass 3. You stick all that in and do some algebra, you get this result down here. I'm going to pause for a second. Any questions on that? One of the tricks I did was just take every single term and multiply it by 2. That gets rid of all these over 2s, over 2, over 2, over 2, and you get stuck with a 2 in front of that. That's where this 2 came from, right there. I multiplied everything by 2. Let's get rid of some of this junk. All right. Okay. So stop me at any time if you do have questions. Let's get that out of here.
I have one question.
Yeah.
So the AC on mass 1 is the same as the A1 we had for mass 1, correct?
Area 1. Yes. Yes, absolutely.
Okay.
So mass 1 right here, the area of this one was, good question. So this was A, right?
Makes sense now.
And this was C. And so that was area 1 was just A times C. Yep. Is that good?
Yeah, that makes sense.
And then I just kind of cut out some steps here for 2 and 3 as well.
Makes sense.
All right, cool. Let me clear that out. Let's get back to here. Based off this, if it's drawn to scale, do we expect it to be a positive or a negative number if this is drawn to scale?
Negative.
Negative. So let's look. This is a skill that takes a little bit of finesse to learn, but how do we know which one of these is bigger? Well, C is clearly bigger than D. That means C squared should be bigger than D squared. A plus B is clearly bigger than A over 3. That means this term, the second term with the negative sign, should dominate and we get a negative result. Everything in the basement is positive. So this makes sense. That is a way to check the sign of your answer. It's not the same as plugging in numbers, but it is checking the sign. Okay. And now suppose some architect wants this shape, but wants the center of mass to be above the origin, right? Maybe they're making a concrete deck and they want the support beam to be right here. Well, they want this thing to be balanced about that support beam. So maybe they want to have this be longer. This gives you an idea of how long you would need to make this thing. And it goes through the math and you could figure this all out. And I did that for you. But if you are a civil engineer or an architect, this center of mass stuff is a huge deal because you want your buildings to have supports, maybe, and that will affect where the center of mass is located, will affect the force on each support. More on that in chapter 12. We will talk about basic statics in chapter 12. That's just foreshadowing. So, okay, that's cool. That's great. And yeah, this one surprised me in some way. So that means it might be actually interesting. My intuition was not correct. If you've ever had that happen to you, where I ask you some question, say, what do you think? And you're wrong. This happens to me too. Okay. Now, let's go on to 9.32. And then maybe we'll be at a good spot for a break, and then we'll come back and do calculus till our brains explode. Okay, so 9.32, I'm going to get this drawn up. Okay. Based off the problem statement, is this a uniform mass or a non-uniform mass? What do you think?
Non-uniform?
Uniform. The default is we are going to assume it is uniform unless the problem specifically tells us otherwise.
Oh.
So that's a good guess, right? And so just turns out center of mass problems, we tend to assume the easier case
Okay.
unless otherwise specified. Cool?
Cool.
Yep. And generally speaking, if you have wood, yes, it is non-uniform because there might be more knots on one side than other, or maybe it's a little thicker or thinner. But on average, it turns out, even if it's non-uniform, the uniform will probably be close to the correct answer anyways. So generally speaking, unless we're specifically told it's non-uniform, we are going to assume it is uniform. And I believe it mentions that. I'm just going to confirm that at the top of page 43. Let's just make sure that's in your checklist. I think I said that somewhere. I forget where I said that, somewhere in there. But generally speaking, unless otherwise specified, assume it's uniform. So now that information is with you.
Yeah, it's there on part D.
Okay, cool. Gotcha. Okay, thanks. Now, in this one, what are we given? We know the radius. We've got this circle. This is the trick that I want you to do. Circle with a square hole out of it. You could try and do calculus on all these little pieces, and that would be tedious. So what we're going to do is say that this is equal to a solid circle with no hole minus, and I'm going to put the coordinate system on here just so I could follow. That's a minus sign. This square hole. And so the idea, we could do exactly the same procedure as before, where we could get x1 and m1, and we could get x2 and m2. And instead of adding them in the center of mass equation, what we're going to do is say x center of mass is equal to, we're going to use a minus sign this time, because this is like negative mass. It's a hole. It's an absence of mass. So it would look like this, x1, m1, and x2, m2 with a minus sign. And that's the only difference. That's a lot easier than doing calculus, in my opinion. All right. So in this case, what is x1?
0.
0. Sweet. So do we even need to figure out m1?
No.
Yes, it's still in the basement. Yeah, I got you. Okay, so how do I figure out this mass? It's a plate Should I use a 1D, 2D, or 3D density? It's a 2D object. Let's use a 2D density. I'll explain that more later. I know that's probably confusing, but I want to use a 2D density. So sigma times what? What's the area of object 1 going to be?
Squared.
Pi capital R squared. Got it. Now, don't overthink it. Let's just start simple. Let's say the side of this square is S. What's x2 going to be? What is the center of mass of that square?
S/2.
S over 2. Positive because it's in the first quadrant. What's the mass?
S².
Sigma
Sigma
S
S squared.
squared. But yes, the area is S squared, so the mass would be sigma S squared, whatever this weird sigma is. More on that later. Now, the only given in the problem was R. So S is not allowable for our answer. How could we, what can we do?
The square touches the end of the circle, right?
Going back to the original picture, you're right. So can you give me some geometry out of that?
Would it be the square root of R? Like
Something like that. Okay, you're on the right track. And do you agree that this side is S, this side is S, and this side is R? If I drew it correctly, I'm really at an angle here. I can't see very well. Do you agree it looks kind of like that?
Yeah.
And so here you could use geometry. You could either use 45, 45, 90, or just know the answer. That's how I do it. I just like, well, can't you tell that R equals square root of 2S? Because that's the known answer from a 45, 45, 90 triangle. Or you could Pythagorean theorem, S squared plus S squared equals R squared. From that, you could figure this out. So there's a couple of different ways, but it suffices to say you could use geometry to figure out this relationship. So notice here we know that S is actually equal to R divided by root 2, which I think is kind of where Alonzo was going there. So he's on the right track. Whoops, let me scoot it back. There we go. At this point, it's literally grab the pieces, shove them in, do algebra. What are some common things we've seen in every single problem? Number one, this is a trick you could sometimes use. Replace a mass with a density times an area, or a density times a length, or a density times a volume. We could use a density to replace the mass with an area calculation. Number two, in every single problem, we've had to do some geometry to figure out where the center of masses are located, or maybe in this case, we had to do a little bit of geometry to find a relationship between the two pieces. So these problems generally use a lot of geometry. That's probably why I enjoy them so much. I just like geometry. It's fun. You could have used trig. Earlier we saw, okay, yeah, more on that later, but this is a common theme. Coordinate system, geometry. All right, and this area trick. All right, so let's go to the solution and see what's up.
So was x1 0 because it's like a complete circle then?
It's because if it is, let me go to the solution because I've got it drawn out there too. Hold on. We were given this shape, and we were told the center of the circle is right at the center of the coordinate system. That's why it's 0.
Gotcha. Okay.
If it's a whole circle, right? Boom, there we go. Is that cool?
Yeah, I gotcha.
Yeah, and now look at this. This shocked me. You cut that huge hole out of this thing, it only shifts it about 7% from the center, less than 7%. That's like right. Hold on, let me zoom in here. Right there. It barely moves the center of mass at all, right? 7% is like 1/14. So that's approximately to scale. You cut that huge hole, and the reason why is you've got all this mass here, but you still have all this mass up here, so it doesn't shift much up and down. Similarly, you got all this mass on the left side, but you don't have much there. So now, all right, that's cool. All right, and that's how you handle the first 3 bullets, I think. Any questions about that? Maybe I'll bring that back up for just a second. Any questions?
I have a question.
Yeah.
So you were able to take out that square and treat it as like the own little thing. Can you say like if there's a shape, can you extend to that shape? Because
Yeah.
like in the previous
Yeah.
problem, it was almost like a rectangle, but it was missing that one piece.
Yeah. Oh, that's interesting. So let me see if I understand you correctly. Like this one?
Yeah.
So yeah, you could actually do this one another way. You could have done that this way. We could have done like this, and then we could have subtracted off a triangle. That would be the same. So you could have done 1 piece, 2 piece, and the 3rd piece would be a triangular hole. And that would also work. And it's probably just as easy. So yeah, that's a great way to do it. Is that what you were asking?
Yeah.
Yeah, that would work. I guess the hard part here is the y coordinate of center mass gets annoying because we were told the coordinate system to use is this one. So it might make sense if you were doing this, you could split it up into 4 pieces. 1, 2, 3, 4. Yeah. Yeah. Good stuff. All right. Keep those questions coming. It's a lot more fun when we interact. So anytime you have a question, go for it. All right. And let me scroll back a bit here. That's not what we want. Suppose you have a projectile problem. That is not what I want right now. Let me go back a little bit here. Page 43. All right. So what have we effectively done right now? We have gone over these till we're blue in the face, and we have kicked the crap out of that. All right. So now, if we have to use calculus, what are we going to do? We've got this procedure to follow. Oh, there it is. Okay. So I accidentally snuck in the comment down there. My apologies for that. So if no comment is made about not, there's that one there. Thank you for pointing that out. And so we need to understand this huge chart. But rather than understand all of this, I'm going to talk about density very briefly, and then we're going to take a break and we'll come back. So let's just talk about this density and the area density really quick. So let's start with a problem like this. Let's say maybe. Okay, let's not. Let's give up, give everybody an A, quit and go home, or try a different. Oh, this marker works. Never mind. Okay. We have a rectangular plate here. Now, obviously, there's some thickness to this plate. So I'll try and actually draw this for once. Sorry, that's a little sloppy there. That's a little better. Okay, so that's supposed to be a triangular plate. Now here, let's say this has length, width, and some thickness here. This dimension I'll call T. Now in all of these problems, you might notice there's masses in them in the numerator and the denominator. The mass of this would equal length times width times thickness times density. Now, if you look at the units of this, this is kilograms. Let me write this in a different color. This thing is kilograms. It's a mass. This and this together, these combine. Let me do it this way. These combine to have units of meters squared. Length times width. That's an area. So now, what if we combine these two units, the thickness of the plate and the density? If we combine those two, we get something that has units of meters times kilograms per meter cubed. That is kilograms per meter squared. That is sigma. So in case you're wondering what this density is, all we're doing is we're grouping the thickness and the volume density together to get rid of one of the dimensions. And if you're saying, wait, is that legal? Well, think about this. We had stuff like this, x1 m1 plus x2 m2 all over m1 plus m2. Whoops. We had stuff that looked like this. Well, if there's a T up here and a T up here, there's a T here, there's a T here, they're all going to cancel out because the thickness would appear in the mass calculation. So that's another reason it's totally fine for us to use this area density, because the thickness, which we don't want to specify in the picture, would cancel out anyways. Now, what if we go another direction with this one? What if we looked at a cylinder? This is supposed to be a uniform cylinder. Okay, so in this case, there's some diameter, there's some length. We know that the mass of this would be density times volume. Well, in this case, that's density times, let's see, pi over 4 diameter squared times the length. Uniform just means constant, Gonzalo. Uniform means, so if I say uniform density, that means that means the density is constant along the length of this rod, say. If I say uniform magnetic field, that means it's constant in size and direction. So uniform is slightly stronger than the word constant, but it basically means, yeah, constant. Is that good enough, Gonzalo?
Yeah, thank you.
Yeah. Uniform, constant, almost exactly interchangeable. Uniform also applies to vector fields. So yeah, maybe that's why physicists use uniform. All right. I think in chemistry, don't they say homogeneous mixture? One that is uniformly distributed throughout? Something like that.
Last question. Is that a P or is that a row?
This is a row. So that's a good question. So capital P looks like this. Lowercase p looks like this. Row looks like that. So it's subtle. The P I draw like this, where it's got a very square top. The row comes down and over. Is that helping?
Yeah.
It looks barely different, doesn't it?
Yeah, like that
Yeah.
little slight tilt is the only way I can tell the difference.
Yeah. And that's the thing. This is why I'm always looking for people's italics in their talks, because you have to all the time be looking at stuff that subtle anyways to do your problems. So you get used to it. It's crazy, right? Don't those look strikingly similar? Yeah. So if you're ever not sure about any of the letters, go ahead and ask just like that, because it's, yeah. So this is rho your density. All right. Going back to the unit check on this, this is kilograms. This is meters. This is going to be kilograms per meter cubed times meters squared. All of this groups into a term we call lambda. Sometimes we call it the lower letter mu. So these would be two different terms used for linear mass density. The idea here is, if you look at this, let me get a better example. Hold on just a second. I got something in the other room that'll work. Okay, here we go. This is just a piece of steel, right? And now there's a point at this end. It's not perfectly uniform, but if we ignore the end caps of this, it's approximately uniform. Okay, meaning there's the same amount of steel in each piece of this rod. Okay, and so in this case, the idea is for every centimeter of length, you'd know how many kilograms are in this piece of steel. And then you might say, well, what if I want to account for that? We could actually put in a non-uniform density to account for that, or cut this into pieces, or draw it in CAD and hit compute center of mass. But that's the idea here. So a linear mass density is how many kilograms or grams per inch or centimeter or meter. The area mass density is how many kilograms per unit area, etc. So let's take a 10-minute break, unless there's other questions. So we'll plan on coming back at 6:36 on my clock, or whatever, 10 minutes from now, all right? I'm going to leave the live stream running just so I don't forget. Any questions? All right, see you in 10 minutes, and we'll pick up the calculus part of this. think we still got one more minute. Hope I'm keeping track of time correctly. There we go. I'll give you about another 30 seconds. All right, so let's go ahead and get into it. All right, so again, we're looking at page 43. We're talking about center of mass. We try to avoid calculus if possible. Now, how do we do problems if we do need to use calculus? Okay, so let's say we have some random looking shape. So let's say this is our coordinate system. And maybe you use, I don't know, maybe you're cutting some sheet metal and it takes some weird shape that isn't easy to break into pieces. Like this. So there's some curvy shape. All right. So what if we want to figure out this one? One thing you could do is approximate it using the first techniques, and that would probably get you pretty close. Depending on what job you needed done, that might be good enough. And that's probably a good first step. But let's say we wanted to get this very precisely, okay? So in that case, we're going to pick somewhere and we're going to slice this object. So we have to do 1D calculus because that's what we know in this class. That's the prereq, 1D calculus. So if I want to get Y center of mass, I need to slice it thin in the Y direction. If I want to get the X center of mass, I want to slice it thin in the X direction. So let's just say I want to slice this thing up really thin in the X direction here. So I'm going to take a slice here. It's not perfect, but the idea is this slice has some thickness, dx. The position of the slice is, in this particular case, it's distance x to the right. Okay. So notice a convenient spot to put the coordinate system is the bottom left corner of any object. Not always, but usually that's a good spot. Okay. Now I'm reading this checklist. It says use the appropriate density equation to figure out what dm is. Now, in this particular case, I'm looking at a two-dimensional object. It looks like a plate. So if it's a 2D object, what I would do is I'd come into here and say, okay, if I'm dealing with a 2D object, I'm going to have a 2D slice. That means I'm going to talk about sigma, the area mass density. If the object is of uniform density, I could get the density using this formula. If it's non-uniform density, we can plug in some equation that we know. Let's worry about non-uniform later. Let's first try and understand uniform density. If we can't understand all the basics with uniform density, we're never going to get non-uniform. All right. Now, by the way, here, if you're curious, these are the types of objects that look 2D to the math. They are thin plates. Okay, got it. Now, and here's some examples of how the uniform densities might be calculated. Remember, it's total mass over total area. In this case, it would be something complicated. So again, we are trying to use an X slice to figure out the X center of mass. Because we have a dx in here, we're going to use this equation right here. Let me show you how this works out. The sum of x sub I, mass sub I, divided by the sum of the masses is our point mass or splitting objects into pieces type formula. When we do this in calculus land, we're going to integrate x dm. dm is the small amount of mass associated with the slice located at position x. I need to divide that by the total mass. In general, that is dm. Okay. Sometimes, well, in general, we know, I should say it this way, always the integral of dm should equal the total mass. In some problems, they give you the total mass and you don't need to do this integral. In some problems, they don't give you, and then you have to do this integral. So we see most of this is very similar if we can just figure out what the heck dm is. So bullet C is the hard one. I'll show you some examples in a minute. In this case, dm would equal sigma times dA. That's a small amount of area. This is kilograms. This is kilograms per meter squared times a small amount of area is still an area times a meter squared. The units check. The issue again comes down to what the heck is dA? Well, dA is the area of a slice. The area of this particular slice is y, the height of the function, times dx. Now, if you go ahead and plug this into these integrals over here, if you just plug that in, notice that we've got an x here, we've got a dx here, but we also have this y. The y is tricky. We must use geometry or math or something to write y as a function of x. If we can rewrite the height as some function of x, everything plugs into the integral. We've got this done. Okay. So if it's non-uniform, we'll do this problem later. Okay. Any questions about this stuff while I have it all up here? Let's get to an example.
Professor
Oh,
Joseph,
go ahead. Go ahead. Yeah.
before we get into the example, I just had a quick question out of topic about the homework check. Is it going to be open from today till tomorrow, correct?
I forget. Whatever it says in Canvas. Yeah.
Okay, sounds good.
Yeah. So, and then remember that one's timed.
That one's timed. Okay.
Yep. Yep. So hopefully you got your technique down from the practice one. All right.
Good. All
Cool.
right. Thank you.
All right. Yep. Okay. Good question. All right. So let's go ahead and do some examples of this now. Now I'm going to start here. I know you all know the answer. We just talked about this. You know the answer from this is 1/3 from the fat end for a triangular plate. But let's go ahead and derive that. And I think a lot of you probably think you know what you're doing, but I think this might reveal there are some subtleties. This is not the same thing as what they do in your math class, okay? So just trust me and listen, will you? All right, so I'm going to draw this up. You can kind of think about it. Turns out physics, there's just some details you got to get right. $9.29. Okay. I'm just getting the picture drawn. I'll catch up in a minute. Not an easy picture to draw. Height, length, and width. Okay, got it. And that, okay, got it. So here's my attempt to draw that picture. We've got a slice sitting over here somewhere. Okay. We're told that this distance right here is y. And I don't know if you could tell, but this thickness here, what's a good name for that thickness?
dx?
dy.
dy.
Now, normally you would think it's dx, right? But look what I did to you on this problem. I said I hat is out of the page, j hat is to the right, and k is up. So I goes to j goes to k, or I goes to j goes to k. This is actually a right-handed coordinate system. It does work out. But, okay, my point here is you got to always watch your axis labels. That's what that's all about. Sorry about that, Alonzo. I got you on that one. All right. Okay, so watch out for your axis labels. Normally, yeah, I would probably do X and Y, but this one, whatever. So based off that, are we setting this problem up to solve for the X coordinate of mass, Y coordinate of mass, or Z, based off what you see here?
The Y?
The Y. So we're going to figure out the Y center of mass. So here's the integral we need to figure out. This problem tells us the total mass. So all I really need to figure out is the integral of y dm. Again, you could say, well, wait, isn't it this, the integral? That's absolutely true. However, the integral of dm is mass. And then I could just pull that out front. So sometimes you'll see it written like this. It's the same math. So, okay, we've got one integral we've got to do. How hard could it be? Okay. Famous last words, right? Okay, so let's read the question. I'm going to get the question up here. The first part says, okay, what are we doing? Okay, determine the density of the slice. Is this uniform or non-uniform density? Did it say? Uniform.
Uniform.
So what's the density going to be? 1D, 2D, or 3D object? It's a 3D object, so I need a 3D density. In this case, that's rho. If it's uniform, that's going to be the mass total over the volume total. Well, what's the total volume of this thing? It's okay to guess and be wrong. It doesn't offend me.
LHW.
L times H times W is on the right track. That would have the right units. Length times width is the area of the base, but think about it like this. What if this is the base and W is the height? What's the area of this base?
HL over 2.
HL over 2 times W. Oh, and there it is. You got it too, Jacob. All right. So we know that this volume is going to be 1/2 of length times width times height. Subtle. All right. Now, in this case, I could even flip this 2 to the numerator and write it this way. So this is the density of this. Again, where did this come from? Total mass over total volume. And because the total volume had a 2 in the basement, I flipped that to the top. So again, it probably looks better like this for understanding, but when you have to use it later, it makes sense to flip that 2 to the numerator. There's our density. Determine the height of the slice as a function of y. Okay. I didn't understand that question there. Mark, if you check the unit, oh, I see. Okay, I got you. Yes, you're right. Oh, okay, Mark, you're on it. Good. All right. So now in this case, let's see. What's next? I want to get z. And actually, let me do this in color. I want to get z, which is the height of the slice, as a function of y, horizontal position in this case. I want to get the height of this slice, z. If you tell me a different value of y, the height of this slice should differ. What I'm saying is we need to do this process in general for more complicated shapes. So even though this may seem obvious, why don't we just say a third from the fat end? Working through this detail is the hard part. So it's important to do that on this simple case. I need the height as a function of y because each different slice will be a different height, right? Over here, they're tall. Over here, they're short. Any ideas?
It's a linear function, right? Like,
It's a linear function. So what's the standard linear function that you know of?
the mx plus b.
Yeah. Okay. So I'm going to change this color to red. What he's saying is this equation is something like y equals mx plus b, except I don't really like this particular way of writing it because, number one, height is supposed to be z, not y. M is usually mass. So what I'm going to do is we're going to change this to z equals slope y plus intercept. The idea here is we could see that the height of the slice is going to vary. We know that the height of the slice is some parameter z. The horizontal distance is y. Maybe if I color code that, it'll stand out even better. So all we really need to do is figure out what the slope is and what the intercept is, and we've got it. So what's the slope?
H over L.
Nope. Close.
L over H.
Nope.
Rise over
Go back to your first one.
H over
Is this slope going up or down?
negative H over.
Got that negative sign. Oh, all right. So rise over run times y plus, let's get the intercept here, plus the intercept. Oops, let me write that in red. Plus the intercept. Rise over run is not h over L. Rise over run is negative h over L because the slope is going downwards. The rise is negative. And what's the intercept?
Where do you use the h?
Yep, just h. Okay. You could factor out an h as well. And that turns out to be kind of useful. So whatever, that's fine. This is a good equation. We're good to go. So now what have we done? We know we're figured out this equation. We know the density if we need it. We know the height. The next step is dm, right? Figure out the mass of this slice. The idea, what are we doing in a center of mass problem? We're taking each position times each mass. I know this one's position in the y direction is y. Now I need the mass of this particular slice. They're not all the same mass. As they change in size, they change in mass. And this will take the weighted average of them, right? So let's go ahead and rock this out. dm should equal, in this case, it's a 3D object. I'm going to use a 3D density times the volume of my slice. So instead of talking about the area of a slice, I need the volume of this slice. In this case, what is the volume of that purple slice? I'm going to shut that door. What do you think? What's the volume of that purple slab? Take a guess. It's okay to be wrong.
Z times dy.
Z times dy would get you this area.
Times
So
W?
W dy.
times W, ZW dy. So this would be ZW dy. I could tell this is right because this has units of kilograms. This has units of kilograms per meter cubed. Meters, meters. That also has units of meters. This is correct. This is in meters cubed. That's a good, this works out dimensionally. Z as a function of y, we could take that and shove it into here. And we've got a function here where the dm in this ugly integral is now all in terms of the letter y and constants. Think about it. 2m LWH, those are all constants. Density is a constant, therefore. W is the width. That's a constant. Z depends on y, but we know how to write that in terms of y. So if I plug this in, Z is a known quantity. We shove that in, we could do this integral. Before we do that integral, what are the limits of integration?
Zero to L.
Correct. The smallest value that y could take is, in this particular problem, 0. In other problems, it could be a negative number, right? Now, the largest value it could take is all the way over here to L. So the integral has limits of 0 to L. Now, what would be different if this was a non-uniform problem? Not much. The only difference is, instead of you having to figure out this equation, I would give it to you in the problem statement. You shove it in, and everything else is the same. So, if you're wondering why I made you go through all this rigmarole and do this in a complicated way, it's because the process we are following here is exactly the same, whether it's uniform or non-uniform. This will work in Physics 162 when you're doing quantum mechanics. This will work in Physics 163 when we're doing charge distributions or current distributions, different things. So I know it seems overly complicated, but I'm trying to show you the most general technique that could be generalized very easily. So yeah, it's ugly, but it's worth it in the long run, in my opinion. That doesn't mean I'm right. I could be totally wrong. It's just my opinion. Let's take a look at the solution and see. We're not always going to go this slowly, but I think the first time it's important to go slowly. Okay. There's our density. Here's our equation of a line. Obviously, if we had a parabola or something, we'd need a different equation than y equals mx plus b, or slope y plus intercept. The slope is right there. There's the intercept. There's the equation. Here I factored it out. Oh, here's something I forgot to tell you. because just like remember Denna said, oh, it's H over L, right? Here's a way Denna could have caught his own mistake without me being there. Always check by plugging in a point or two. So when you write down your equation of a line, always check it. When you stick in y equals 0, this drops out, the L's cancel, and I get H. That's a good sign. If we plug in that y equals L, if you plug in y equals L here, or y equals L here, notice this with the minus sign gets the correct result, whereas the one that Denna suggested originally, H over L, does not. And so, Denna, I guess I'm trying to tell you that this is a way you could check your work later, is always check a couple of points. So my apologies if I'm belaboring that more than I need to. Check a couple of points every time you write an equation and make sure it works. Next, we've got a 3D slice, so we use dv. We've got, here's my density. Here's this. Oh my gosh, it's some big ugly mess, whatever. Before you do the integral, check the units. This is units of kilograms. It's a tiny amount of mass. It's a dm. dm means tiny amount of mass. Well, a tiny amount of mass is a bunch of numbers times a tiny amount of width. Okay, it's going to be tiny. This is kilograms per meter squared. This is meters squared. So I get kilograms. It looks good. You plug it all in, we get some big ugly mess. It works out. We get 1/3 from the fat end. So now that we've done this triangle, never do it again. Just know the answer for a triangle, please. All right. Oh yeah. So we see this. Got it. All right, so let's go take a look at this one now. Let me look at this picture. What we have now figured out is the center mass here. Let's see, that's about halfway. So that's about 1/3. That's where the center mass lies, on that portion, right? Let me just do that. So we know the center mass is going to be on the center line, somewhere right about there. It's really hard to draw this. Sorry about that. It's 3D. But the center mass is going to be somewhere there. So my question to you now, which side is going to have more mass? Side 1 of the red line or side 2? Or do they have the same? What do you think for a triangle?
Side 1.
Side 1. And so remember, center of mass does not mean same mass on each side of the line. Excuse me. So if we go into here, if you're curious, I actually worked it all out and figured this out. And all right, so people have this tendency to believe that there's the same amount of mass on the left and right side. And it turns out even for this simple problem, that's just not true. We are going to cover this more in chapter 10. All right. And so here ends up being the coordinates for center mass. It's very similar to what we just did. So that's good. I hope this number makes sense. It's halfway in the X direction. Let me just bring up that picture one last time. We expect the center of mass will split this dimension right down the middle, right? We expect there should be the same amount of mass on the left and right of that line. And then we know it's 1/3 of the fat end, 1/3 of the fat end, and then halfway in. So it's somewhere right in there. Sorry, this is so goofy to draw in 3D. All right. What do you think so far? Good? Oops. Come on, Zoom. What's going on? Oh my gosh, it won't let me maximize this window. All right, whatever. Zoom. There we go. All right, so let's go to center of mass. Here's one. What are we effectively doing in this problem? This. Whoops. Oh, did I move this? Oh gosh, I moved the camera angle. Hold on. All right, so this is what it's going to look like in code. There's a bunch of stuff here, but this is not the way you're going to do it. Let me just comment this out. Ah. All right, whatever. Sorry. Ah, geez. All right, hold on a second. Try to do everything one-handed. It's killing me here. There we go. All right, so let's see if this runs better now. The idea is you're building this thing up out of these vertical slices, right? So you could kind of see them there. And again, this isn't perfect, but if I edit this program, let's just set the length to, okay, the length in this one is 6, the height is 3. And let's do this with, say, 11 slices right now. Okay. So this is what you're doing in calculus, right? You're splitting things into slices and just adding them up. And now if I scroll down to here, the answer should be 1/3 from the fat end. So the answer should be 2 and 1. Because again, I used a length of 6. 1/3 of 6 is 2. 1/3 of the height, which was 3. So it's not perfect, is it? But if we go to more and more slices, it should get closer to what we expect. Notice it's a little bit closer. And so if I go to 100 slices, notice it's very, very close to what we would expect. So we expect a value of 2, 1, 0 for the center of mass. It's getting very close, but notice what is the trade-off? This is starting to take a while to process, right? It's looking more and more like a triangle because we used more and more slices. That's what you're doing in a calculus class. And I don't know if that helps you visualize where 1/3 from the fat end is, but there it is. All right. Now, I don't know. Any questions while I've got this up? That's what calculus is. Splitting that cylinder, or sorry, splitting that. Whoops. Oh my gosh. Come on now. We're splitting this into chunks. And literally each one of those chunks in this problem has the same density, but they have slightly different masses because they're slightly different lengths. So the mass dm and the volume associated dv are all different, but the density is the same. All right, let's get out of there. All right, let's stop the share. I've got too many windows open. All right, let me get rid of this. Wait, let me move it. I'm getting lost here. Okay, there we go. Get that out of here. Let's get back in and look at another one. Whoops. Just got a screen share. It's too bad spring break doesn't last for infinite time with paychecks. Wouldn't it be nice if we were all getting paid lots of money to just sit here and do nothing? I'll work on that. I'll work on that. I don't know how to code that one up. Okay. Yeah, right. We're working on that. We'll get it done tomorrow or the next day. Okay, so let's look at this one. All right. Take a second. You go ahead and do what you think, and I'm going to go ahead and get it drawn up. Okay, 9.30. Almost there. Okay. When you look at this problem, are we trying to get the x coordinate center of mass or y coordinate center of mass?
Why?
Yes, exactly. So now we're back to our normal coordinate system. So in this case, is this a 1D, 2D, or 3D object?
2D?
2D. You could tell that because the problem says it's 2D. However, there's a key word in the problem in case you want to know how to do this when I don't tell you exactly what it is. Plates generally are 2D objects, okay? So that means, should I be using a lambda, kilograms per meter, sigma, kilograms per meter squared, or rho, kilograms per meters cubed as my density? Do I want lambda, sigma, or rho for a 2D?
I think it was sigma.
Sigma is correct. Okay, which has units of kilograms per meter squared. That's going to be the most convenient for this problem. All right, so now in this case, oh, we've done parts A and B already. Okay, cool. In terms of only y and r, I need the area of my slice. So you probably know this, right? dm is equal to sigma times dA. This is the mass of my slice. This is the density. And this is the area of my slice. So if I have a tiny slice, I have a tiny mass, but my density is not tiny. It's just could be 19.6 kilograms per meter cubed if it's whatever. All right, so if we want to stick this in the integral, we need to understand this in terms of the dimensions. So help me out. Help me with the area of my slice. How would you get that area? And you don't have to try and do it all in one step. You could define a parameter first, and this is a good trick. Don't try to do it all in your head. Like, what do you want to call this? This distance right here. Just give it a name.
D.
D. All right. D is kind of a bad one because DD and stuff might appear.
Oh,
So
yeah.
I'm like, it probably would work out, but let's avoid the letter D. Pick a different letter.
L.
Okay, L. That's fine with me. So that is distance L. Okay. What shape is this? What does it look like to you? Is it a circle? Is it a square? Is it a triangle? What shape does that slice look most like?
A trapezoid?
Okay, a trapezoid. And then I'm going to be really lazy and call it a rectangle.
Oh.
So you're right. So let's keep it easy. You could do a trapezoid. By the way, if you do a trapezoid, your codes would converge more rapidly. Remember that I had to go out to 101 and I still had a little mistake? If I had done a trapezoid to figure out the height, it would have converged more rapidly. But whatever. So your trapezoid would be better. Let's keep it easy because we could use computing power to do the rest. So, okay, it's a rectangle. What's the area of a rectangle?
Length times width.
So we know length. So what's this dimension called?
dy.
dy. It's the tiny amount of y. So what's the area of this slice?
L dy.
L dy. So now comes the hard part. L is not the same for every slice. If you choose a different value of y, the length of this slice would have to change. So you need to tell me what L is in terms of y and this constant radius that we were given. So how can I get that?
The negative parabola?
It's not a parabola. It's a circular plate.
But
Excuse me, half circle. You're on the right track. So he's saying, wait, couldn't I just say it relates to this parabola? And I said, no, it's got to relate to this circle. What's the equation for a circle?
pi squared.
That's the area of a circle, but we need the shape of the curve, right? Remember last time we had a triangle like this, and what we had to do is get a function for one piece of that side. Well, now we've got a circle. I need an equation that represents that shape.
Circumference.
Okay, Jacob's on the right track. X squared plus y squared, that's not an equation.
Oh, equals r squared. Oh,
Okay.
yes.
So how does L relate to X? I'll give you a hint. This is X.
2x.
2x. So couldn't I solve this equation for X? Whenever I take the square root, I need to think about the plus minus. In this case, I'm going to choose the positive root because I just want a length. And then I double that. That's what L is. L is 2 times this. Why do people hate this? Because you got to know everything you were ever supposed to know. Yeah, that's kind of hard. I expect you to understand the formulas for these things, right? And so you're lucky that this class is online so you can just Google shit. So yeah, you guys are spoiled. Whatever. If class ever goes back in person, everybody's just going to fail in droves. Whatever. We'll handle that when we get there and we'll pick it up then, right? Every teacher will just have to pick it up at that point. All right. So let's look at the solution before we get too depressed. All right. So, whoops, that's not the solution. Here's the solution. All right. Let me make this a little wider. Here we go. This is good. This is good. This is the hard part, isn't it? Using reality to come up with an equation on your own instead of somebody spoon feeding it to you. Oh, you have to use logic and thought. Oh, it's the worst. Now, once you get that, it's pretty straightforward. dm is this. Here's the center of mass integral. And notice this density, it's going to factor out. We don't even need to compute it. If you wanted to compute it, let's do it just for practice. In this case, it's uniform, right? We know this is a uniform. That allows me to use mass total over what for an area density? Is it length total, area total, or volume total?
Area?
Area total. What's the area in this case? What's the area for this shape?
1/2 pi squared.
Yep. And then just like last time, the 2 could be brought upstairs. But as you can see, there's a density here, a density there. These are going to factor out, then cancel out. What are the limits of integration I should use for this problem?
Negative x to x. Or
What are we integrating over? dx, dy, or dz here?
dy.
So what is the smallest value of y that makes sense in this picture we've drawn?
Will be 0.
0. And what's the largest value that makes sense based off that picture we drew?
R.
Yeah, nice. Is that good for the limits? Does that make sense, I mean? So let's go down into here. And on an exam, I'd give you a table for that ugly mess. But for this class, I'll just say use Wolfram Alpha if you can't figure it out. So, all right. If you care, when you see stuff that looks like this, That makes me think of stuff that looks like a triangle. That makes me think of a trig sub. So if you didn't know to use a trig sub here, the shape of these is what gives it to you. You think about geometry and you could just see the trig sub popping out. So I did it if you care. I did it all for you. But notice look at this number, 0.4244. Got it? So basically about 0.42. Let's go into here. Man, I don't know what is going on with this. Let's run this one. Whoops. Okay, let's take a look at it. So let's start it small again, 11. So again, if our radius is 1, we expect the answer should be 0.42. And let me make these things smaller. Whoops. Sorry, I gotta use 2 hands here. I'm so slow. I don't know what I was thinking. Let's do 2.2, 2.2. This will just make it less zooming once I start here. So it's just adjusting the coordinate axes so the thing will be zoomed in right. Okay, so when I run this one, there it is. Okay. We see the center mass is about a little less than halfway up. When I look at the number, I got 0.39. That's pretty close. If we check this again with 21, it should get closer to, what did we say it was? 0.424. And it starts to look more and more circular, right? And then let me do this too. Whatever. Let's jack this up to 101. And so when we run this thing, now we've got a whole bunch of these. It's looking very, very circular. This is the calculus process. I don't know what the disk method is from calculus class. This is basically slices, one-dimensional slices, right? So if you look in here and we really zoom in, each one of these is just a horizontal slice. See that? And so there's a whole bunch of these horizontal. Okay, so if that's what they call it, then that's what it is. Now look at this. Look, there's a little defect there. You see that? Look, it's kind of rounder right here. So it's having some trouble doing this calculation right. Something's not quite right here. Maybe it's my axes aren't centered right. I don't know. But something looks a little bit off here. But the idea is, and maybe I need to double check this one, but it's approximately correct. So maybe I need to shift them all by half a unit, right? But if you look, here's that kind of the guts of the code. And so, all right, so we'll do this in lab later. So we're going to do it a little bit easier way than this. So this way used to kill people. So here's that shifting, and I don't know. Let's talk about this stuff in lab later. So that said, we've got 10 minutes left. All right. So if you're curious, this starts to work out. And so you cut something up finer and finer, and you could make these. And yeah, there's some numerical artifact there. We could worry about that later. All right. We talked about these 1D problems. We haven't done any yet. The 9.33s. Take a look at these. Here are some with uniform and non-uniform. And here's one right here where there's some mass on the left and some mass on the right. So notice your limits will not always be 0. This limit might be negative L/2 to positive L/2. Right? You could have different limits than 0 to L or 0 to R. All right. Here's one where it's non-uniform. Think about this. This says What does non-uniform mean? As X gets bigger, the density gets bigger. I tried to show that with shading. There's not much stuff here. There's a lot of stuff here. If it was uniform, the center of mass would be right in the middle. Now we're saying there's more mass out at the end. That's going to shift it out this way a little bit. We expect a non-uniform density would shift things. And notice you can always get total mass with this equation. The process is exactly the same as the uniform case. The only difference is instead of having to derive the density using total mass over total length or total mass over total area or total mass over total volume, we just use the equation that's given to us. Notice, in order to understand this problem, you're going to have to figure out the units of alpha so that you could check your units. Keep going. Here's one where it's some arbitrary power. So this is a variation where I gave you the length and I gave you the center of mass, and then I say, okay, figure out the exponent. So that's just a variation on this one. It's actually straightforward if you do it. Maybe you're wondering, what about this non-uniform density? Is this reality? This shows you one way you could get a non-uniform density in reality. I took different amounts of aluminum and I glued them on here in strips. And I actually did this with a piece of lumber. And the idea is I just cut a chunk of this and I figured out the density of this end, and I called that lambda L for left end. I figured out the density of this, lambda right end. And then I said, okay, I should be able to figure out the density. It looks like it's varying linearly, approximately, but not exactly. It's approximately linearly. So that means my density is a function of X. So it would be equal to slope X plus intercept. And then what do? We do the same thing that we did with the triangle, right? And you say, okay, well, now my density is varying linearly. I don't have some geometry, but I do have some numbers. You could do a little bit of trial and error and plug in numbers and see if you get it to work out. And I figured this out and it matched up with reality. That's cool. If we go into here, here's an ugly one, but I say, just set it up. Don't finish it. Right? Just see if you can get it to that point. This is a cool one. Here's one where you have a parabola instead of a line or a circle or that weird thing that we just did, the non-uniform density. So there's one for that. Here's one with a hole in it and a uniform rod, and you put it all together and there's a fractional power. So you've got lots of variations on this. Notice this is a challenge. So if you want to see how to do that, you could do that. Here's another challenge. If you want to see it, that's how you could do it. All right. And then here's an arc. We haven't talked much about arcs, but if you want to do an arc, dm is just lambda times ds, and ds would be a small amount of, let me just show you here. Okay, so let's say we take a small piece of this. That length right there is ds. Okay, now notice, I can't really draw this very well, but there's a small angle inside of there, and then there's the big angle outside. ds is related to r times d theta, the tiny angle inside. The arc length of the entire piece is r theta. But again, if you have a differential on one side of the equation, you need a differential on the other side of the equation. So if we're trying to get a tiny amount of arc length, that's the radius times a tiny amount of angle, a d theta. That's where this comes from. Now, yeah, there's some work there. And if you're curious, this is very similar to the Fosbury flop. I think I worked this one out somewhere. Let's go to here. Whoops, wrong one. That's a hemisphere. That's kind of cool too, if you're curious. Whatever, that was not what I wanted to do. Where's that arc? Oh, there it is. I think I clicked the wrong button. There it is. So notice the center of mass is actually inside the arc. And the idea here, why is this useful? This is the high jump problem, right? If you're a high jumper, why do you do that? You're basically shooting your body over like a projectile, but the center of mass of your body always stays below the peak of your body. So if you're trying to jump and the center of mass is actually right here, as you jump over the bar, your feet are hanging low and you're shooting over like a projectile. Your center of mass height is the upper limit of what is physically possible. By bending into the shape, you move your center of mass slightly outside of your body and below it. So you could actually get over a bar that's higher by first putting your head over, and then your head gets lower. And so this doesn't violate physics. You could jump over a bar that is above your center of mass. So the bar could be located right here, and your center of mass is right there. No physics is violated, but you can get over a higher bar than just jumping over in a straight line. So that's kind of cool. And what do we got? 2 minutes left. Let's see if there's anything else to say. Oh, this is a fun one. When you see this one, you could actually do two right triangles. You could take a right triangle and cut a hole out of it with another right triangle. And so if you're curious, what if you have some non-right triangle? Well, you could make non-right triangles out of right triangles and piece it together. All right. And then we'll pick up zombies in a canoe later. We'll do that next time. We'll just stop here. Oh, whoops. I'm not screen sharing, am I? Shoot. Sorry. Sorry about that. I'm tired. Just going back here. So this is the one I was just talking about, the Fosbury flop. We talked about that one. And then this one is, if you had a non-right triangle, you could view that as a right triangle that's big and cutting out a smaller right triangle. Basically, you could build non-right triangles out of right triangles. And then, like I said, we'll pick up zombies and canoes next time. That'll be our next. This is critical learning for the society. We need to know about zombie canoe problems. Sheesh. All right, let's